Thought we start out today with a compelling video. This is a fossil fuel burning plant, and fossil fuels obviously spill significant amount of gases, including CO2, into our atmosphere. In fact, in 1 year, there's an estimated amount of CO2 that could fill up 10 million Olympic-sized swimming pools going up into our atmosphere per year. Is this something we want to continue with? School near Chernobyl, where the uh, nuclear fusion plant blew up a number of years ago. Did we sign up for this? This will be out of service for a couple hundred years before people can go back to this school in this particular area. So today's topic, which we will talk about in detail, surrounds the concept: is there a scalable green energy source that could be used across the globe? And the argument today will be yes, there is. And we're mainly going to focus on the fuel to produce that scalable green energy. This is not to uh, reduce the concept of using solar or water or wind, but those are not scalable across the globe by far, and they also have their own issues. Today's discussion is entitled Lunar Helium-3, and it's the key to unlocking quantum computing and worldwide green energy. This magical isotope, lunar helium-3 or helium-3, is impossible to source on Earth in quantity, and it's essential for our future. And I appreciate the chance to talk today at the Mining Critical Minerals Conference. Our company is singularly focused and only focused on the extraction of helium-3. Our company is LH3M, or Lunar Helium-3 Mining. There are three use cases which we're going to talk about for helium-3. My background is fairly eclectic. The green area or the green box focuses on those types of backgrounds educationally that relate to helium-3, specifically planetary geology and mechanical flight test engineering and engineering mining and aerospace engineering. All of those have given me a core fundamental knowledge of what it's going to take to go to the moon to extract helium-3 successfully. Here is the agenda for today. We're going to talk about why we're even talking about this topic at this conference, why go to the moon, where you get helium-3 from, why do you care? In other words, what are the use cases, revenue projections, because we're going to make a case to go to the moon to extract helium-3. So there better be a fair amount of revenue to offset the expenses. And then we're just going to touch on some extraction challenges. Okay, why are we talking about helium-3 at this conference? First off, helium-3 in its present form is not a mineral, but it's still a resource. And presently today, as you're going to see, there are use cases on Earth now that cannot be fueled or used with helium-3 because there's not enough of it, making it a critical resource now. But in the future, as nuclear fusion comes on board and quantum computing expands, we need helium-3 for both of those things, making helium-3 not just now, but even more so in the future, a critical resource. There are two main reasons to go to the moon. The first is well known. That could be for scientific research, global competition, preparation to go to Mars. That would be a cost center in which governments pay for this. It doesn't generate any revenue. And that's how a lot of space science is done. That's how Apollo was done in the 1960s and 70s. But that's back in a time when many governments, including the United States, had a much better financial outlook, back when the world was captivated by the space program, and that was before cell phones, most computers, handheld videotapes like TikTok and others, so the world was not distracted back then. It's a different time. I would make the argument that the cost approach to going to the moon, in which government pays for this, which is ultimately paid for and approved by the taxpayer, is not going to continue in a long-term fashion. I just don't think the public will be able to put up with this or approve this when we have enough issues going on. That's the bad news. The good news is, unlike in the 1960s and 70s, there is another much more compelling reason to go to the moon. This is a revenue generator reason. Ultimately, this would be borne by private entities. Maybe there's a private public start, but ultimately, when done correctly, this could be a permanent, large, long-term reason to be on the surface of the moon that would be a revenue generator, a business case. Helium-3 is an isotope of helium, and if you look at the yellow box or bullet point, that's the most important thing. It's got very special use cases on Earth. Up until now, helium-3 on Earth has come from the decay of nuclear weapons production using tritium. The estimated US supply is less than 10 kilos, and I would argue probably much lower than that. That's not much. Helium-3, in addition, naturally comes from the sun. It travels in the solar wind, and on Earth, it's captured by our atmosphere. So basically, there's none of it on the surface of the Earth of any consequence. On the moon, it's been baked into the ground because there's no atmosphere for billions of years. The good news is there's a wild estimate of 1 million tons of helium-3, which is more than enough to power nuclear fusion reactors for hundreds of years on Earth. The bad news, or the news you have to be aware of, is the concentration is very low. It's somewhere between 1 and 15 parts per billion. Another slide on sourcing, the graph in particular. This is just a version of the United States supply over the past couple decades. If you look at the green dashed line, the top point, the highest point was in 2000. Again, this is a byproduct of weapons production, and the supply has dwindled down dramatically. You can't mine it, and there is some ideas that you could potentially produce a very small volume of this in something called a D-to-D fusion reaction, but that would be a low yield, difficult to scale up process. This makes the source of helium-3 the most likely source of helium through the moon, with an estimated 1 million tons. That could be as low as a couple 100,000 tons to a couple million tons. It's a lot. There's many different hypotheses of how helium-3 is retained in the ground. Now, the ground of the moon is called the regolith. So the dust, the dirt, the rocks are basically collectively called the regolith. The bulk of the helium-3, for the most part, is most likely in the top layers of the regolith because it came from the solar wind and the energy of impact is very minimal. So it probably does not go down that deep, the bulk of it, that is. There's probably some particles of helium-3 deeper down when the moon had a lot of turnover from meteorites a couple billion years ago. So there's probably the bulk of it at the surface, loosely bound. There are some that are deeper down, more than likely less concentration, that are chemically or somehow mechanically attached to crystals or other minerals. Okay, let's look at present use cases of helium-3. This slide is only about the existing use cases. The most important is radiation detection. Basically, to detect nuclear bombs at borders, the best way of doing this was with helium-3 as a radiation detection component. The third column over is the amount of helium-3 we estimate was used in the United States in 2008. These are rough numbers. In total, it's probably close to 10 kilos. In the last couple of years, as the supply has dwindled, the amount of helium-3 available is minimal. So even for border security and border detection, many of the new radiation detectors are not using helium-3 because they can't source it. Now we're going to get into the big future cases of helium-3, nuclear fusion, which is going to require a fair amount of it for green energy. And then the one after that will be for quantum computing. Less of a volume, but a much more strategic governmental issue. A fun slide. If you drive an electric car, some people think they're driving a green car. Well, that may be true, but it depends on where the electricity comes from. The bulk of electricity does not come from green sources. So if you're driving an electric car, more than likely you're not driving a green car, which is a fallacy in many places across the globe, especially in the United States, where governments and municipalities buy electric cars thinking they're buying green. Ultimately, the source of electricity is 70–80% is produced by burning fossil fuels or through nuclear fission. And who would have ever thought of some of these things? Did we ever suspect that the amount of fossil fuels being burned produces this much carbon dioxide and carbon monoxide going up into our atmosphere. On the nuclear fission side, was it ever really discussed that we'd have to store radioactive waste for more than 100,000 years? 100,000 years. And in the US, there is no central storage facility for this waste. In addition, there's a potential for catastrophic explosions. You just have to think about Chernobyl to think about that problem or that count nuclear fission. Let's take a little bit deeper dive on fossil fuels, in particular coal. Right now, the world burns really roughly about 8.8 billion tons of coal per year, but it's not magical. You have to get it out of the ground. To get it out of the ground, you have to remove the soil above the coal, and that requires energy. If you used energy produced by coal, you need about 0.36 billion tons of coal just to remove the overburden to get down to the coal. And then most coal is not used next door in a power plant. Most of it has to be transported. So rough numbers is uh, if you had to transport your coal, what you do, you use enough energy. That's about 0.24 billion more tons of coal to create energy to move that coal, if that makes sense. Ultimately, you need coal to get coal. You need about 9.4 billion tons of coal per year. Some of that's used to mine coal, to transport it, and ultimately to burn it or to create electricity. It creates a lot of different types of fossil gases or carbon or gases, greenhouse gases. One of them in particular, carbon dioxide. There's about 39 billion tons of CO2 waste produced per year. As I mentioned earlier, that's enough to fill about 9 to 10 million Olympic-sized swimming pools with gas every year going into our atmosphere. There's no doubt that that causes some harm. And then we come back to nuclear fission. These barrels are being stacked up at different fusion plants across the United States and across the globe. There is, as I mentioned, no central storage facility in the United States. It was never built. And again, we have the side effects such as explosions. Here again is a schoolhouse near Chernobyl. This schoolhouse is within 30 kilometers of Chernobyl, and that within 30 kilometers circle is unsafe for 2 to 300 years. There's also been deaths from Chernobyl and cancers. I would suspect there is more than 5,000 cancers which have been reported. It's probably a higher number than that. Okay, that was all the bad news. Let's turn to the good news. The future source of electricity is most likely going to come from production. I'm sorry, nuclear fusion, not to be confused with nuclear fission. Fusion is a reaction in which two or more atomic nuclei combine under extreme temperatures, temperatures hotter than the sun, for example. And ultimately, you're going to get more energy out than you put in. That's the key thing. If done correctly, you're going to get more energy out than goes in. Two major reactions. Deuterium and tritium produces helium-4, a neutron or N plus energy. We've coined that nuclear fusion 1.0. Deuterium, which again is easy to obtain for the most part. And if you had helium-3, that would produce also helium-4, this time a proton and energy. We call that fusion 2.0. The pros of fusion in general is it cannot explode. There'll never be another Chernobyl. And we're not that far off into the distant future. The first commercial small contract for nuclear fusion energy will come in 2028. And we're going to start to see over the next 10 or 20 years mass production of fusion plants across the globe. We predict the nuclear fusion will replace nuclear fission and fossil fuels. The question is nuclear fusion green? It's a very important slide to answer that question. The setup for this slide in the middle is a column of tritium. So if you used tritium as your fuel source, or fusion 1.0, that's the middle column. And if you had helium-3, that's the column to the right. No one knows how really to scale up the production of tritium. That would have to come from mining lithium. You take your lithium out of the ground through a fission type of reaction, convert it to tritium. Then when you put tritium into a nuclear fusion reaction, the waste products have to be stored for up to 100 years. The neutron that comes out of a nuclear fusion reaction produces more damage and causes more reactor and human damage than what would happen with a proton. If you had helium-3, it's scalable from the moon. There's cool thing is there's no waste products to store. It kicks out a proton, not a neutron, so it's safer for humans and for the reactor. So if you had helium-3 for your fusion reaction, you're creating scalable green energy. In fact, some people believe, and this isn't us, but fusion companies that are working in this space believe with helium-3, you can get a nuclear fusion reactor down to the size of a football. Can you imagine having that to power your car? High, a high level picture of development. On the left-hand column, nuclear fusion with tritium. There's been billions spent by more than 40 companies, more than 10 countries. They're moderately far along with this. On the helium-3 side, we're in the infancy of this fuel source off the surface of the moon. If the world switched to fusion only, got rid of fission and fossil fuel burning, and you powered it just with if you powered it just with helium-3, first off, if you switch the market from fission and fossil fuels over to fusion, you don't have a brand new industry. You're substituting one for another, and that's a $40 trillion roughly industry for electricity production. That's really rough numbers. That came from Bloomberg. Now, going deeper, if you took your fusion reactors and you only use helium-3 to power them, you would need about 570 metric tons across the globe to power fusion using helium-3. The next use case for nuclear fusion is quantum computing. Quantum computing is advancing very rapidly. I love this example. If you had a string of numbers that was 2048 in length, and you try to break it into its prime components called factorization, it would take a classical computer 10,000 years to do that calculation, whereas a quantum computer can do it in much less than a day. The speed is just mind-boggling. The applications are both good and bad, potential cancers, cures, drug discoveries, and politically depends on who has it. This could allow one country or groups of countries to be dominant over another by building strategic defensive and offensive weapons. Helium-3 is related to this because it's used as the coolant. Quantum computers have to be cooled down to 0.01 Kelvin to function correctly. The only way to get it to that temperature is with helium-3. The average quantum computer is going to need somewhere between 1 and 10 liters roughly of liquid helium-3 in their lifetime. No one has estimated how many there will be in existence, but we did this just to put a number out there. If we estimated there would be 10,000 quantum computers 15 years from now, that is a demand of helium-3 of about 4 metric tons. There's significant national security and strategic implications for the United States and our allies. That company or that country or countries that has quantum computing over another set of countries or country will have strategic dominance, which can make a big difference in the balance of power. Without helium-3, these computers, again, cannot be cooled down to 0.01 Kelvin. One single slide on revenue, because revenue is going to drive the ability to offset the cost if this is to be a private business. Today's helium prices are about $30,000 a gram or $30 billion a ton. That will fluctuate up or down based on market conditions. Ironically, tritium costs more than this. So fully baked in across the globe, if you powered the world with fusion and helium-3, you'd need about 570 metric tons, which is more than $17 trillion worth of revenue per year. Now, I suspect that price will go down as we use fusion for electricity, so people's prices in their electric bill is not astronomical. And I suspect the initial prices of helium-3 for quantum computing will be higher. In any case, we're still looking at trillions of dollars, and the numbers for quantum computing, while not in the trillions, are still in the $100 billion range. Let's look at some of the technical challenges. This presentation is not designed to get super far into the weeds, but enough so you can understand this is not going to be as simple as taking a miner truck from Earth and going to the moon. First off, let's look at the competition again, or who's talked about helium-3. China has returned samples just like the Americans did from Apollo. China's returned samples and announced they want to go to the moon to extract helium-3. I'm going to surmise they want it for quantum computing first. India is farther behind in their space program, but catching up. The United States has made no public opinion about this. They intend to go to the South Pole mainly for research to look for water and rocks. China and the United States are in some sort of parallel race to put humans back on the surface of the moon. I suspect that we should be going there for a resource, which is helium-3, not so much to plant a flag. There are private companies that have announced their intent to extract helium-3, including ours. The big difference about ours, we believe, is we are focusing on the lunar environment and working with it and not against it. That topic will become clearer in some of the upcoming slides. A very important slide when it comes to a private business. Private businesses cannot survive by just printing money or borrowing money. Eventually, they have to make money. The success of making money when it comes to helium-3 and bringing it back to Earth will require three things. The reduction in cost of transportation going to the moon will need to come down. Fusion will have to be commercialized and switched over to helium-3. And to the bottom right in red for a reason, you have to go to the moon to use lunar techniques and not bring up Earth-based techniques to extract helium-3. This is a picture of a gold mine in Australia. Has nothing to do with the moon. This is an example of how mining is done across the globe. This is an open pit mine. There's also mines that are purely underground. In any case, the formula or the method of mining is the same. You somehow blast or grind up the ground to extract your ore. You then process your ore by making it smaller, treat it with chemicals or heat, and you try to extract out your precious resource and you dump out the back end. The wasted rock cause tailings. In this case, in this gold mine, the precious resource is gold, and you're going to dump out the back wasted tailings to extract gold. Now keep in mind this particular picture, and here's an artist's rendition of what mining on the moon might look like for helium-3. This looks nothing like the last image. However, the mining technique is identical. In the front is a grinder wheel or bucket wheel designed to grind up the ground down to depth. The ore is then transported through conveyor belt inside and processed, usually by heat. And out the back end, you dump wasted rock and you hold on to helium-3. This requires, in this schematic, a fair amount of energy and a lot of moving parts, which is an Earth-based technique, and we will argue will fail, we believe, on the surface of the moon. Here's some of the challenges that were sort of reflected in that schematic that I just showed you. First off, the concentration of helium-3 on the moon is very low. At 1 to 15 parts per billion is an estimate compared to Earth-based mines such as a copper mine at 0.5 per 100. Therefore, if you used an Earth-based technique to extract 1 part of usable helium-3, you would need to dump out the back end 999 million parts of unusable tailings. The energy cost of this is impractical and frankly just not doable. We've recognized that and we've come up with a low energy lunar solution that will extract helium-3 with the least amount of energy and was again designed for lunar conditions and in particular designed for the concentration of helium-3 on the surface of the moon. The second challenge is going to be the dust itself. Again, the dust is called regolith. It's not like Earth-based dust. The moon has never had water or wind to erode rocks or dust, and therefore dust, it looks the same as it was 4 billion years ago. It's sharp and spickly. It's high in silica, like 45% in silica. It's charged and can levitate above the ground from the solar wind, and there's a fair amount of iron related to the regolith. Ultimately, it's extremely clingy and abrasive. If you look back at some of the lessons learned from the past, specifically from the Apollo astronauts, Gene Cernan, the last astronaut on the surface of the moon, if you paraphrase what he said something like this: I think we can overcome other physiological, physical, and mechanical problems, but if we don't address the dust, you're not going to survive. Another slide about this dust issue. If you look back to Gene Cernan's last mission, which was Apollo 17 in 1972, there were two astronauts on the surface. They spent 22 hours walking around collecting samples, and in just 22 hours apiece, look at the damage it did, including eroding 3 of 12 to 15 layers of Harrison Schmitt, the other astronaut's boot. Look at the picture. That's Harrison Schmitt, the astronaut who was a geologist. That's supposed to be a white spacesuit, and it is gray. So the way to address the dust is to try to come up with a system that will repel it, but equally important to use the least amount of moving parts. The more moving parts, it's more likely going to fail, requiring repair. And we've come up with, again, a solution to mine helium-3 with very few moving parts. Another challenge is that the atmosphere on the moon is virtually a vacuum, whereas on Earth it's one atmosphere. If you heat the regolith and you allow gas to come out of the ground, in particular helium-3, in a vacuum, it will go shooting off at ballistic speeds, whereas on Earth it's more contained and sort of hovers. Our mining process, therefore, respects that. So when we heat the regolith, we have a skirt around our rover to prevent the gases from escaping out into space itself. We want them directed up through our mining system. Consequently, we also want to minimize the disruption to this skirt. And one way to do that is to have a unique bi-directional plow that's never been seen before. It directs the rocks, the loose ones that is, around and behind the rover. It's not going to take care of all of them, but it should take care of some of them. Here's another schematic of that idea. If you look where number 1 is, the rocks are going to hit a unique bidirectional plow. They get directed to a channel, which is channel 2. They go around, and then they get put out behind the rover 3. So they go around and behind the rover to prevent some of the rocks from going underneath the rover or going over into the next mining field when the rover comes back down. When we designed our company, we designed it with a systems engineering approach. We took a blank sheet of paper and said, if we were to design a mining approach on the moon to extract helium-3, how would we do it? And how would we work with the environment of the moon? The low concentration, the abrasiveness of the regolith, and the vacuum location, the vacuum atmosphere of the moon itself. We have a diverse set of engineers, as well as scientists and business people, with the goal of trying to understand the moon as much as possible. We've given numerous presentations in the past 12 months or so to fusion conferences, quantum conferences, space conferences, policy conferences, mineral conferences, and energy conferences. The intent is to get people aware that it is possible to extract helium-3 from the moon to bring it back to Earth. We have an extensive patent portfolio, both in the United States and soon to be international. And this schematic kind of shows where we focus. If you look at the graph, you'll see a rover at the bottom with 5 steps. Our main focus is to target what happens underneath the rover, from trying to identify the concentration of helium-3 at the surface and below it in the subsurface, to heating the regolith, separating the gases that come out of it, because there'll be more than just helium-3, collecting these gases, in particular helium-3, and then taking helium-3 gas and converting it to compressed liquid form for return back to Earth. We've begun strategic relationships with other companies because this will take a huge mass of people and companies to actually do this. But our singular focus is what's underneath the rover. We want other companies and partners to take care of things such as rockets, mobile space stations, EVA suits, relationships to governments. So our focus is underneath the rover. In summary, there's an estimated 1 million tons of helium-3 on the surface of the moon. That's enough to power fusion for a long period of time. The major use cases coming up are to make truly green scalable energy, and the only way to do that is fusion with helium-3, not fusion with tritium. And then there's quantum computing, which is super fast, which is a strategic issue from one country or countries to another. In total, the revenue off of these two use cases is staggering. In order for this to be successful, three things have to take place. Transportation costs will have to come down. As fusion gets adopted, we need to be able to switch over to helium-3. And in red, for a reason, you have to use lunar-based mining techniques, not Earth-based techniques. Our company is singularly focused on this endeavor. We are focused on the extraction process. However, the extraction of helium-3 is just the tip of the spear for what we believe will be a large lunar economy. The vision is when it's fully functional, we might see more than 50 to 100 or more commercial rovers on the surface of the moon and a number of people or astronauts on the surface of the moon in support roles. I appreciate you allowing me to present today. If you have any questions, please ask or visit our website at lh3m.com, lh3m.com. Thank you.